So what we have in Pumapunku is the traditional, what I would say, Eric von Däniken tackling archaeology. There is, within the methodology of how these stones were constructed, never attained in the surrounding landscape of Tiwanaku.
The stones at Pumapunku have always felt wrong, too precise, too far ahead of their time. For years, those massive H-shaped blocks were treated as a mystery we could admire, but eventually explain, until now. Because when researchers 3D-scanned these stones, they didn't just map the surface, they uncovered what's hidden inside.
Pumapunku is so unique in the way that it was constructed that it is the most intriguing ancient site on the planet.
And the deeper they looked, the less sense it made. Perfect internal joints, seamless interlocking cuts, angles so exact they don't just suggest skill, they suggest design. And here's where it turns unsettling. These blocks were carved over 1,000 years ago.
But we have been unable to date the stones of Pumapunku themselves. They could be thousands, if not hundreds of thousands of years old. We don't know.
Long before anything close to modern tools existed. Because if these blocks were made the way they appear to be, then either history is missing something big or we've been asking the wrong questions the entire time. Pumapunku and the Tiwanaku civilization, Pumapunku, translated as Gateway of the Puma in the Aymara language, forms part of the Tiwanaku ceremonial complex near Lake Titicaca. This high-altitude center sustained a dense population through raised field agriculture, hydraulic control, and coordinated labor organization. The broader cultural context reflects technical competence rather than improvisation. However, Pumapunku introduces a level of architectural precision that diverges from other Tiwanaku constructions. Spanish chroniclers in the 16th and 17th centuries described the site as wondrous but unfinished. The description aligns with the current archaeological condition, a terraced platform disrupted by seismic activity and subsequent material removal. Large stone elements remain scattered rather than collapsed in situ, indicating structural disassembly rather than simple degradation. No complete reconstruction has been achieved despite prolonged archaeological efforts, suggesting that key structural relationships between blocks remain unresolved. The most distinctive architectural elements at the site are the H-blocks. Each block is a monolithic unit, typically measuring approximately 97 by 99 by 55 centimeters and weighing over 600 kilograms. The defining H-shaped plan consists of two vertical sections connected by a central bar, but the functional complexity lies in the surface engineering. These blocks incorporate recessed channels, stepped profiles, notches, and blind cavities that terminate within the stone rather than passing through it. Such features indicate mechanical intent rather than decorative carving. The geometry implies interlocking interfaces where alignment and contact precision would be necessary for structural stability. Archaeological evidence supports this interpretation. Copper alloy I-shaped clamps have been recovered at the site, indicating the use of metal fasteners to secure adjacent stone elements. This introduces a hybrid construction logic, combining lithic precision with metallurgical joining techniques. Material selection further complicates the analysis. The majority of finely worked H-blocks are composed of andesite, a dense volcanic rock with a Mohs hardness between 6 and 7. This significantly exceeds the hardness of copper tools, which average around 3 on the same scale. Under such conditions, copper implements would deform and wear rapidly during direct cutting. Effective shaping of andesite typically requires either sustained abrasive processes or the use of harder intermediary materials. The logistical dimension reinforces the anomaly. Geological sourcing studies indicate that the andesite originated from quarries located tens of kilometers away, often across or around Lake Titicaca. Transporting multi-hundred-kilogram blocks across uneven terrain at high altitude implies coordinated labor systems, load distribution strategies, and route planning. However, transport complexity does not directly account for the observed finishing precision. Surface analysis reveals an inconsistency in production signatures. Certain unfinished or partially shaped stones display characteristics associated with percussion techniques, irregular surfaces, pitting, and uneven contours consistent with hammerstone use. In contrast, completed H-blocks exhibit flat planes, consistent edge definition, and minimal surface irregularities. The transition between rough shaping and final finishing lacks continuous intermediate markers, creating a discontinuity in the manufacturing sequence. Experimental archaeology provides partial insight but does not fully resolve this gap. Replication attempts using copper tools, stone hammers, and abrasive sand have demonstrated the feasibility of surface smoothing and basic shaping, particularly on softer lithologies such as sandstone. However, these methods encounter significant limitations when applied to andesite, especially within confined geometries such as recessed channels and internal corners. Abrasive techniques require space for tool movement and debris clearance, while percussion methods inherently produce surface damage inconsistent with the uniformity observed in finished blocks. Dimensional comparisons across multiple H-blocks reveal a pattern of constrained variability. While not identical, similar blocks share proportional relationships and recurring geometric features. This suggests the presence of a design framework guiding production, even if absolute standardization was not achieved. Such a framework implies measurement systems, spatial planning, and possibly the use of templates or guides during fabrication. Interpretations of this evidence remain contested. Early 20th century researcher Arthur Poznański proposed a significantly earlier construction date based on astronomical alignments, though subsequent radiocarbon analyses placed the primary Tiwanaku activity between 300 and 900 AD. More recent commentators, including Christopher Dunn and Brian Forster, emphasize the apparent mismatch between observed precision and conventional tool assumptions, arguing for under-recognized technical capabilities. Within established archaeological discourse, the prevailing model maintains that cumulative labor, abrasion, and iterative refinement can account for the observed results. However, this model does not fully explain the uniformity of internal features or the absence of expected tool signatures in confined spaces. The discrepancy between material hardness, tool limitations, and achieved geometry remains an active point of analysis. So what are we actually looking at? The 2024 scans that changed everything. In late 2024, a geoarchaeology team introduced a tool that had never been used at Pumapunku before: structured light 3D scanners. This matters because traditional measurements, rulers, calipers, and even laser distance tools only capture selected points. Structured light scanning captures everything. It projects a grid of light onto a surface and records how that grid bends across every tiny bump and edge. The result is a dense point cloud, a digital copy of the stone accurate down to extremely small units. The level of precision matters. These scanners can detect differences as small as 0.01 millimeters. That is smaller than the thickness of a human hair. At that scale, surface irregularities that are invisible to the eye become obvious. Slight slopes, tiny dips, or uneven cuts all show up clearly in the data. What the scans revealed immediately challenged expectations. Large exterior surfaces on several H-blocks showed planarity within roughly 0.05 millimeters. In simple terms, those faces are almost perfectly flat across their entire span. For comparison, many modern construction surfaces, like concrete slabs, often exceed that level of variation. Angles were equally consistent. Internal corners measured very close to 90 degrees, with deviations often under 0.1 degrees. That level of angular accuracy is not random. It suggests controlled shaping rather than gradual approximation through repeated hammering or grinding. The most critical data came from the interior grooves. These are narrow, recessed channels cut into the blocks, areas that are difficult to access and even harder to shape consistently. The scans showed that these grooves maintain nearly identical depth along their full length. with variations of around 0.1 millimeters or less. The walls of these grooves are parallel. The floors are flat. The transitions between surfaces are sharp, not rounded. This combination is difficult to achieve even with modern hand tools unless guided by fixed systems. Without guidance, tools tend to drift slightly, especially in confined spaces. A key point is tool behavior. When a handheld tool is used repeatedly, small inconsistencies accumulate. Pressure changes, angles shift, edges wear down. These effects usually leave traces, slight waviness, uneven depth, or irregular spacing. The scan data from Pumapunku shows minimal evidence of that kind of variation in the finished interior features. This has led to a specific observation repeated by multiple analysts. The surfaces appear controlled in a way that resembles machining rather than manual shaping. That does not imply the use of modern machines, but it does highlight a mismatch between expected tool signatures and observed results. Comparisons help clarify this. In modern manufacturing, CNC machining produces surfaces with consistent tolerances across repeated parts. Those tolerances often fall within hundredths of a millimeter, depending on the process. The scanned H-block features fall into a similar range for flatness and consistency, especially considering the material involved. That comparison is not about claiming identical technology. It is about highlighting similarity in outcome. When two very different processes produce similar surface behavior, the underlying control mechanisms become the focus of analysis. To make this visible, digital overlays from the scans are often used. A point cloud model, made of millions of measured points, can be converted into a mesh and then compared against ideal geometric shapes. When this is done with the H-block grooves, the deviation from perfect geometry is minimal. At Pumapunku, that consistency appears in multiple blocks, similar groove widths, similar depths, similar angles, not identical, but constrained within a narrow range. This suggests that the process, whatever it was, could be repeated with limited variation. The 2024 scans do not solve the mystery. They refine it. Instead of general impressions, there is now measurable data. Flatness, angle deviation, and depth consistency are all quantified. That shifts the discussion from speculation about appearance to analysis of geometry. And the geometry introduces a constraint that cannot be ignored. The interior features behave as if they were produced under controlled conditions that limit variation to very small margins. Any explanation must account for that level of control while remaining consistent with the material properties of andesite and the environmental conditions of the site. That is the point where the conversation changes. Not because the scans introduce new speculation, but because they reduce uncertainty about what is actually present on the stone. Why the interior joints defy explanation. Inside Pumapunku, the real mystery is not the big stones sitting in the open. It is what is hidden inside them. Deep inside the H-blocks are narrow grooves with sharp corners and straight walls that meet at almost perfect right angles. This sounds simple at first, but in stonework, this kind of geometry is extremely hard to achieve with hand tools. When stone is struck with other stones or chipped with copper tools, the material naturally breaks in uneven ways, and corners usually become rounded instead of staying sharp. This is exactly what is seen in many other ancient sites, including well-known Inca walls. Even where the stones fit tightly together, the edges still show slight rounding and surface irregularities. That is the natural result of pounding and abrasion. At Pumapunku, however, the finished interior corners of the H-block grooves do not show the same level of rounding. They appear unusually crisp, especially considering they are deep inside the stone where access is restricted. The grooves themselves create an even bigger problem. They are not shallow marks on a surface. They are deep, narrow channels carved into extremely hard rock, and their walls remain parallel over long distances. That kind of consistency is difficult to maintain because any small shift in tool angle changes the shape of the groove. A slight tilt makes one side wider than the other. A small change in pressure makes the depth uneven. Over long distances, these small errors normally accumulate and become visible in the final shape. Inside these grooves, there is also a major access issue. A tool has to reach into a confined space, stay aligned, and remove material evenly along the entire path. At the same time, stone dust and debris build up inside the groove, making the surface harder to control. In most hand-carving situations, this leads to uneven textures and irregular surfaces. Yet when these grooves are scanned, the walls appear unusually consistent, and the floors remain very flat, with minimal variation in depth. The material being worked on makes the problem even harder. The stone used in many of the H-blocks is andesite, a volcanic rock with a hardness between 6 and 7 on the Mohs scale. Copper, which is often suggested as the primary ancient cutting tool, is much softer at around 3. That means copper would wear down quickly when used against andesite. It would not maintain sharp cutting edges for long, and it would struggle to shape hard stone efficiently without heavy reliance on abrasives like sand or crushed rock. Abrasive techniques can smooth surfaces over time, but they also have limitations. They work best on open, flat areas where the material can be moved freely. Inside narrow grooves, abrasive particles can clog, shift unevenly, and create inconsistent pressure. This usually results in subtle waves, uneven depth, or surface roughness. Experimental archaeology has demonstrated these effects repeatedly when trying to replicate ancient stonework using copper tools and abrasives. At Pumapunku, the expected patterns are not fully present in the finished interior features. The grooves do not show strong signs of random variation or rough correction marks in the final state. Instead, they appear controlled, as if the material removal followed a consistent path from start to finish. This creates a gap between what should normally happen with known tools and what is actually observed in the scanned geometry. Another major factor is repetition across multiple blocks. Several H-blocks show grooves with similar widths, similar depths, and similar internal angles. They are not identical in every detail, but they fall within a very tight range of variation. That level of consistency suggests that some form of guiding system or standardized method may have been used during production. Without such a system, manual work tends to produce more variation from one piece to another. At the same time, the working environment adds difficulty. The site sits at roughly 12,800 feet above sea level, where oxygen levels are lower and physical endurance is reduced. Precision work in such conditions becomes more difficult, especially when combined with heavy labor tasks like transporting and positioning multi-hundred-kilogram stones. Maintaining fine control over carving under those conditions is not impossible, but it increases the challenge significantly. Experimental archaeology has tried to reproduce these features using known ancient methods. Researchers have used copper tools, stone hammers, and abrasive sand to replicate grooves and surface finishes. These experiments can produce smooth stone surfaces and basic geometric shapes, especially on softer materials. However, when applied to hard stone like andesite, and especially inside narrow internal grooves, the results tend to fall short of the precision seen at Puma Punku. The interiors often show uneven depth, tool marks, or less consistent wall alignment. One of the most important observations is the absence of expected tool signatures in the most precise areas. In stone carving, tools usually leave behind microscopic evidence such as scratches, chatter marks, or directional wear patterns. These traces help archaeologists identify how a surface was shaped. In the finished interior joints of the H-blocks, these signatures are reduced in the most critical areas, even though they appear more clearly in rougher, unfinished stones nearby. This creates what can be described as a gap between process stages. Rough shaping is visible, intermediate work can be inferred, but the final precision stage, especially inside the grooves, does not show a clear transition that matches known tool progression. That discontinuity is what makes the interior joints difficult to fully explain using standard models of ancient stoneworking. Researchers like Christopher Dunn have pointed out that the consistency of these internal features resembles controlled manufacturing more than freehand carving. Brian Forster has similarly emphasized the difficulty of reconciling copper-based toolkits with the observed internal precision, especially in confined spaces where control is hardest to maintain. Mainstream interpretations still argue that long-term effort combined with abrasive techniques and skilled labor could eventually produce high levels of precision. This explanation relies heavily on time, repetition, and gradual refinement rather than advanced tools. However, the main challenge with this view is the confined geometry of the grooves, where maintaining consistent control is significantly harder than on open surfaces. The result is not a simple contradiction, but a constraint. The interior joints of the H-blocks place strict limits on what kinds of processes can realistically explain them. Any valid explanation must account for sharp internal corners, consistent groove geometry, material hardness, confined access, and repeatability across multiple blocks at the same time. The digital resurrection. The way Pumapunku is being studied has changed completely in recent years. Instead of only looking at broken stones on the ground, researchers now build full digital versions of the site using laser scanning, drone photogrammetry, and high-resolution 3D modeling. These scans are so detailed that every surface of a block can be measured down to fractions of a millimeter. What this means in practice is simple. The ruins can now be rebuilt inside a computer before anyone tries to move a single physical stone. Once the fragments are turned into digital models, something unexpected becomes possible. The H-blocks can be rotated, aligned, and tested for fit in virtual space. This removes the biggest limitation of real-world archaeology, which is the impossibility of physically reassembling massive, damaged stones without risk or error. In digital space, every block becomes movable, testable, and comparable. As these reassembly tests progress, patterns begin to appear that are not obvious on the ground. The blocks are not random in shape or design. They show repeated proportions, recurring groove positions, and consistent notch placements. These are not exact copies of each other, but they are constrained within a narrow design range. That kind of repetition is important because it suggests rules behind the design rather than one-off artistic carving. In engineering terms, this starts to look like a system of standardized parts. Certain grooves and recesses appear in multiple blocks in similar positions, which means they could potentially connect in more than one configuration. That kind of flexibility is not accidental. It usually comes from designing components to work interchangeably within a larger structure. When digital models are assembled, another pattern becomes visible: alignment. Some blocks seem to follow shared directional lines, almost as if they were designed to fit into a larger geometric framework. This is not about perfect symmetry everywhere, but about repeated relationships between angles, spacing, and load-bearing points. Prefabrication means making parts in advance, often in controlled conditions, and then assembling them later. Modern construction uses this method all the time, but it requires planning, measurement systems, and quality control to make sure every piece fits correctly. The scanned data suggests something similar may have existed here in concept, not identical modern technology, but a way of thinking where stone components were produced according to shared design rules. That would explain why different blocks still behave like parts of a larger system, even when they are scattered and broken today. One of the strongest clues comes from load simulations. When engineers test how reconstructed models handle weight, certain block shapes appear to distribute force in predictable ways. Some elements act like stabilizing supports, while others behave like locking or connecting units. This kind of behavior suggests that the shapes were not only aesthetic, but also functional within a structural system. In some reconstructions, the platform even begins to look like a layered framework. Interlocking stone units may have worked together to resist movement, especially in a region where seismic activity is common. Instead of relying on a single massive structure, stability could have come from many smaller, well-fitted components working together. What makes this more striking is the level of consistency across the system. While no two blocks are perfectly identical, they share enough geometric constraints to suggest controlled production. This is where the idea of standardization becomes important. Standardization does not require machines. It requires rules, measurement methods, and repeatable processes that keep variation within limits. That does not mean everything was perfect. Small differences still exist between blocks. Some grooves are slightly wider. Some edges are not exactly aligned. These variations matter because they show human involvement. The system is not machine perfect, but it is not random either. It sits somewhere in between, controlled, but still handmade. This is where digital reconstruction becomes powerful. It reveals patterns that are hard to see when stones are scattered. When everything is reassembled virtually, hidden relationships between blocks start to appear. Axial lines run through multiple structures. Certain gateways align in ways that suggest intentional spatial planning. Even the spacing between blocks sometimes follows repeating intervals. The result is not a final answer, but a shift in perspective. Instead of thinking only about carving techniques, attention moves toward design systems. The question is no longer just how the stone was shaped, but how the entire set of shapes was planned in the first place. Christopher Dunn has argued that the consistency seen in these digital models reflects a level of control that is difficult to explain through simple craftsmanship alone. Brian Forster similarly points out that repeated geometric patterns across multiple blocks suggest structured planning rather than purely ad hoc construction. These views are debated, but they highlight a key issue. Repetition itself needs an explanation. Mainstream archaeology tends to interpret this repetition as the result of long-term development. In that view, builders gradually refined their techniques over time, slowly improving consistency through experience rather than formal design systems. That explanation is possible, but it struggles to fully account for how tightly some dimensions and interfaces repeat across separate blocks. What digital reconstruction changes is visibility. It does not invent new evidence. It reorganizes existing fragments into a form where patterns become easier to detect. That shift matters because it turns scattered ruins into something closer to a readable system. The deeper implication is not that Pumapunku suddenly becomes fully understood, but that it starts behaving like a structured design problem rather than a purely broken ruin. Once the fragments are digitally reassembled, the site stops looking like random destruction and starts looking like an incomplete assembly. That does not solve the mystery. Instead, it sharpens it. Because a system of modular, interlocking stone components implies planning at a level that must account for geometry, transport, and assembly at the same time. Whether that system was fully developed, partially inherited, or experimentally attempted remains unresolved. What the digital models do make clear is this: the blocks were not just carved objects. They were designed to interact. Underestimating the ancients. The scans do something important. Even if they do not fully solve the mystery, they take Puma Punku out of the world of speculation and into measurable reality. Instead of guessing how impressive the stones look, the data now shows exact values for flatness, angle accuracy, and groove consistency. That shift matters because precision can now be compared directly to known engineering limits. What remains unresolved is the method. The scans describe what exists, not how it was made. That gap is where interpretation becomes difficult. The most cautious explanation is that Tiwanaku builders used known tools, stone hammers, copper implements, and abrasive sand, but applied them with far more control, patience, and skill than is usually assumed. In that view, what looks extraordinary is still human craftsmanship pushed to an extreme. A stronger but more controversial interpretation is that some techniques may no longer be fully understood, not necessarily lost advanced machines, but missing parts of a technological chain. Better abrasive materials, specialized jig systems, or shaping methods that did not survive in the archaeological record. Stoneworking traditions can disappear without leaving clear traces, especially when later cultures build differently or reuse materials. A broader pattern supports caution in interpretation. Other archaeological sites have also forced re-evaluation once modern scanning tools were applied. In the Maya region, LiDAR surveys revealed massive urban networks hidden under forest cover, changing assumptions about population density and planning. In classical archaeology, the Antikythera mechanism showed that complex gear-based computation existed far earlier than expected. Egyptian granite carving, especially in hard stone structures, continues to challenge assumptions about ancient tooling capabilities. These examples do not prove a single shared advanced ancient technology. Instead, they show a recurring issue. Limited survival of evidence often leads to an underestimation of past capabilities. When only fragments remain, modern frameworks tend to fill gaps with simpler explanations, even when the remaining artifacts suggest higher complexity. At Pumapunku, environmental conditions add another layer. The site sits at an extreme altitude with thin air, cold temperatures, and difficult terrain. Quarry sources are located miles away, requiring transport across challenging landscapes. Even if precision carving techniques were simple in principle, scaling them under those conditions would require strong organization, planning, and coordination. This is where interpretation becomes balanced. The evidence does not require abandoning known human capability, but it does require accepting that ancient engineering systems may have been more structured than commonly imagined. Precision stonework at this level does not emerge from randomness. It implies intention, repetition, and control over the process. The most grounded conclusion is not mystery, but incompleteness. The scans expand understanding, but they also highlight missing context, tools, workshops, training systems, and construction sequences that are not preserved in the archaeological record. Without those pieces, a full reconstruction of the method remains out of reach. The structured light scans from 2024 provide something rare in archaeology: precise measurement of an ancient problem. The H-blocks at Pumapunku show geometry that aligns closely with modern expectations of controlled manufacturing, flat surfaces, consistent groove depths, and sharply defined interior corners. These are not vague impressions. They are quantifiable features. The central tension remains clear. The physical evidence shows a level of precision that challenges simple explanations based only on copper tools and stone hammers. Yet no confirmed alternative technology has been identified in the archaeological record. That tension is what keeps Pumapunku from being resolved into a single narrative. What becomes more important than answers is perspective. The site demonstrates that ancient construction systems can exceed modern assumptions when viewed only through surviving tool categories. Skill, time, repetition, and possibly unknown intermediate techniques may have combined to produce results that appear unexpectedly precise today. The broader implication is not that history needs rewriting, but that it needs recalibration. The stones do not suggest impossibility in a literal sense. They suggest missing context in a technical sense. Every measurement taken from the site increases resolution on what was done, but not yet on how the full process operated from start to finish. The blocks remain in place on the high plateau, exposed to wind and time. But through digital scanning, they are no longer just broken stone. They become structured data points forming a pattern that can be studied, compared, and tested. And within that pattern, one message stays consistent. Ancient construction was more capable, more organized, and more complex than surface appearance once suggested. Pumapunku still refuses to give up all its secrets. The 3D scans reveal precision that challenges simple explanations, yet the method remains unclear. The stones stand as a record of advanced planning or lost knowledge, still not fully understood. If this deep dive added something new, like and subscribe for more investigations into ancient engineering mystery. Drop a comment with your theory and stay tuned for the next one.